June 6, 1944. As dawn broke over the English Channel, the largest armada ever assembled began its assault on Nazi-occupied France. 156,000 Allied troops stormed the beaches of Normandy in what would become the most pivotal military operation of World War II. The images are seared into history. Soldiers wading through chest-deep water under withering machine gun fire, landing craft disgorging tanks onto blood-soaked sand, paratroopers descending through flak-filled skies. But these dramatic moments, as heroic as they were, tell only half the story of D-Day. Behind every soldier who set foot on those 5 Normandy beaches stood an invisible army that never fired a shot. Logistics officers, quartermasters, transportation specialists, and supply planners had spent 2 years orchestrating what military historians now recognize as the most complex supply operation ever conceived in human history. D-Day wasn't simply won by courage and firepower. It was won by an unprecedented mastery of logistics that would revolutionize military operations forever. The scale of the operation defies comprehension. Over 5,000 ships and landing craft crossed the Channel that day, from massive battleships providing fire support to tiny Higgins boats carrying 36 men each. The armada stretched across miles of ocean, carefully choreographed to arrive at precisely the right moment. In the skies above, 11,000 aircraft flew sorties, dropping paratroopers, towing gliders, bombing coastal defenses, and providing air cover. Waiting in England and loaded onto ships were 50,000 vehicles, ranging from jeeps to bulldozers to Sherman tanks, all needing to reach French soil in working order. But these numbers, staggering as they are, barely scratch the surface of the logistical nightmare facing Allied planners. The true challenge wasn't just moving men and equipment across the Channel, it was sustaining them once they arrived. Consider the mathematics of invasion. Each soldier required food, water, ammunition, medical supplies, spare clothing, and countless other items. Multiply that by 156,000 men on the first day alone, then factor in that within weeks the Allies planned to land 2 million soldiers in France. Each would need roughly 66 pounds of supplies per day. That's 132 million pounds of material flowing into France every single day, not counting the fuel, ammunition, and spare parts needed to keep thousands of vehicles operational. The problem was brutally simple. France had no functioning ports in Allied hands. The Germans controlled or had destroyed every major harbor along the northern coast. Cherbourg, the nearest deep-water port, was heavily fortified and wouldn't fall for 3 weeks. Le Havre and other ports were either too far away or too damaged to be useful. Traditional military doctrine said you couldn't sustain a major invasion without capturing a port first. But waiting to capture a port would give the Germans time to reinforce, potentially dooming the invasion before it began. Allied planners faced an equation that had never been solved before. How do you supply the largest invasion force in history across 100 miles of open ocean with nowhere to unload ships? How do you build a supply chain from scratch in hostile territory while fighting one of the most formidable armies ever assembled? How do you do this knowing that failure means not just military defeat, but potentially losing the war entirely? The answer would require rethinking every assumption about military logistics. It would demand innovations in engineering, transportation, and supply management that didn't exist yet. It would mean inventing new technologies specifically for this single operation. And it would require a level of planning detail so meticulous that officers were calculating individual rifle rounds and counting individual tins of rations months in advance. In the build-up to D-Day, southern England transformed into the world's largest military supply depot. Entire forests were harvested to build packing crates. Warehouses stretched for miles, stacked floor to ceiling with everything an army could need. Ammunition dumps were camouflaged across the countryside, each carefully separated to prevent chain reactions if bombed. Vehicle parks held tens of thousands of trucks, tanks, and jeeps in neat rows, waterproofed and ready for the channel crossing. The organizational challenge was immense. Every item had to be tracked, cataloged, and loaded in reverse order of need. The first things required in France had to be loaded last, so they'd come off the ships first. Medical supplies, engineering equipment, and ammunition took priority. Personal luxuries like cigarettes and chocolate were luxury items that would arrive later. This combat loading principle seems obvious now, but in 1944 it required completely reorganizing how militaries thought about logistics. Planners obsessed over details that would seem absurd to outsiders. How many rolls of barbed wire per mile of defensive position? How many gallons of water per soldier in summer heat? What's the failure rate of radio batteries in damp conditions? How many spare tank treads per armored division? Every calculation had to account for Murphy's Law operating at industrial scale. Supplies would be lost to storms, enemy action, accidents, and simple confusion. Planning required building in massive redundancy. The weather added another layer of complexity. The Channel is notoriously unpredictable, with storms capable of smashing landing craft against beaches and swamping smaller vessels. Planners needed specific conditions: a full moon for paratroopers, low tide to expose German beach obstacles, and relatively calm seas. These conditions aligned for only a few days each month. Miss the window, and the invasion would delay for weeks, potentially allowing German intelligence to discover the plan. Then there was the deception campaign. While assembling the largest invasion force in history, the Allies had to convince Hitler it would land at Calais, not Normandy. This meant hiding the true scale of preparations in southern England while creating phantom armies in the east. Supply dumps and vehicle parks had to be disguised. Radio traffic was carefully managed to suggest troops were concentrating in the wrong areas. Even the logistics of deception required meticulous planning. Perhaps most remarkably, Allied planners knew they'd have to supply this massive force without using traditional ports for months. This reality led to innovations that would define the entire operation. If France had no functioning harbors, they'd build their own and bring them across the Channel. If pipelines couldn't reach France, they'd lay pipes on the ocean floor. If roads couldn't handle the supply flow, they'd create dedicated truck routes operating around the clock. The problem was brutally straightforward. Without a deep-water port, the Normandy invasion would suffocate within days. History offered no solutions. Every major amphibious operation had relied on capturing an existing harbor quickly. But Normandy's geography and German defensive strategy made that impossible. Cherbourg, the nearest major port, sat at the tip of the Cotentin Peninsula, heavily fortified and wired for demolition. Even in the best-case scenario, it would take weeks to capture and months to repair. The Allies would be trying to supply 2 million men by unloading ships directly onto beaches, a method that could handle perhaps 10% of their needs. Military theorists had studied this problem for years and reached the same conclusion. It couldn't be done. Beaches were too vulnerable to weather, tides, and enemy action. Without piers, ships couldn't unload efficiently. Without breakwaters, waves would smash landing craft and damage supplies. Without the infrastructure of a modern port, the entire invasion would grind to a halt as soldiers sat idle for lack of ammunition, food, and fuel. But in May 1942, after the disastrous raid at Dieppe demonstrated the impossibility of capturing a defended port, Winston Churchill issued a characteristically bold directive to his military planners. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. Churchill's solution was audacious to the point of seeming absurd. If France had no usable harbors, Britain would build complete artificial ports and tow them across the English Channel. Not temporary docks or improvised piers, but full-scale harbor facilities capable of handling the same traffic as major commercial ports. The project was codenamed Mulberry, and it would become one of the most remarkable engineering achievements of the war. The scale of the Mulberry harbors staggers the imagination. 2 complete portable ports would be constructed, designated Mulberry A for the American sector at Omaha Beach, and Mulberry B for the British sector at Arromanches. Each harbor, when fully assembled, would be roughly the size of Dover, England's busiest port. Together, they needed to handle 12,000 tons of supplies and 2,500 vehicles daily, and they had to be ready by D-Day. The engineering challenges were immense. A functional harbor requires breakwaters to calm the sea, piers for ships to dock, and roadways to move cargo ashore. All of this had to be built in sections small enough to tow across the channel, yet strong enough to withstand Atlantic storms and the 6-foot tidal range of the Normandy coast. The components had to be assembled by military engineers under fire in unfamiliar waters, with the entire invasion's success depending on getting it right the first time. British engineers developed a brilliantly modular design. The outer breakwater would consist of massive concrete caissons called Phoenix units, some standing 5 stories tall and weighing 6,000 tons. These hollow concrete boxes would be towed across the channel while floating, then deliberately sunk in precise positions to create a protective barrier. Additional protection came from bombardin units, massive cruciform steel floats that created a floating breakwater in deeper water. For the innermost protection, the British scuttled 60 obsolete ships, known as gooseberries, to form additional breakwaters. The piers presented their own engineering puzzle. Traditional fixed piers were impossible given the dramatic tidal range. The solution were floating pierheads, massive steel platforms that rose and fell with the tide while remaining anchored to the seabed. These connected to shore via flexible roadways called whale units, floating steel bridges mounted on pontoons that could accommodate the tidal movement while allowing trucks to drive directly from ships to beach. Construction began in late 1943 at sites across Britain. The operation required unprecedented industrial mobilization. 20,000 workers labored in shifts around the clock. Concrete for the Phoenix caissons consumed the output of entire cement works. Steel for the roadways diverted material from other war production. Shipyards built the caissons in massive dry docks, then floated them out to staging areas where they awaited D-Day. The secrecy required was extraordinary. German reconnaissance flights regularly photographed British ports and coastlines. Cover stories explain the massive construction as replacement piers for bomb-damaged docks. Phoenix caissons were built in plain sight but disguised as harbor repairs. The true purpose remained one of the war's best-kept secrets. German intelligence never imagined the Allies would attempt something so ambitious. As D-Day approached, the components assembled at designated ports. Hundreds of Phoenix caissons floated in British harbors, looking like enormous concrete boxes. Miles of floating roadway sections waited in estuaries. The old ships designated for scuttling received final preparations. Thousands of tons of anchor chains and concrete blocks stood ready, and the tugboat crews who would tow this massive fleet across the channel rehearsed in British coastal waters. The cross-channel operation began immediately after the initial landings. Starting on D-Day +1, tugs began the arduous task of towing the Mulberry components across the channel. Phoenix caissons, wallowing low in the water, moved at barely walking speed. The steel roadway sections followed in long trains. Old ships steamed to their final berths under their own power. It was a naval operation nearly as complex as the invasion itself, with hundreds of vessels crossing the channel in carefully orchestrated sequences. Assembly began in chaos. Engineers worked in water often still swept by German artillery fire. The first task was sinking the Gooseberry ships to create initial sheltered areas. Naval crews deliberately grounded and scuttled 60 vessels in precise locations, creating instant breakwaters. Meanwhile, tugboats positioned the massive Phoenix caissons. Once in position, valves were opened and the caissons flooded, slowly settling onto the channel floor in predetermined patterns. The work was dangerous and exhausting. Engineers worked in diving suits on the seabed, checking caisson placement. Construction crews assembled the floating piers, while German snipers occasionally fired from the bluffs. Everything had to be done quickly because the invasion's success depended on getting supplies flowing immediately. There was no time for careful engineering, only rapid improvisation under combat conditions. Within 1 week of D-Day, both Mulberry harbors were partially operational. Ships could tie up to the piers and unload directly onto the floating roadways. Trucks drove from the pierheads across the whale bridges to the beaches, creating a continuous flow of supplies. The harbors weren't beautiful, but they worked. Liberty ships that previously took days to unload while anchored offshore could now discharge cargo in hours. Then, disaster struck. On June 19th, the worst channel storm in 40 years descended on Normandy. For 3 days, hurricane-force winds and massive waves battered the harbors. Mulberry A, the American harbor at Omaha Beach, was devastated. Phoenix caissons broke free from their moorings. Whale roadways twisted and buckled. Pierheads tore loose and drifted onto the beaches. Ships dragged their anchors and collided. When the storm cleared, Mulberry A was a twisted wreck of concrete and steel, effectively destroyed. Mulberry B at Outre-Manche survived, though badly damaged. The British harbor's more sheltered location and slightly different configuration saved it from total destruction. Engineers immediately began repairs, salvaging components from the wrecked American harbor. Within days, Mulberry B was operational again, now handling supplies for both British and American forces. The loss of Mulberry A forced the Americans to rely more heavily on beach operations, but the success of Mulberry B proved the concept. For the next 10 months, the Outre-Manche harbor operated continuously, handling an average of 7,000 tons of cargo daily. By the time conventional ports came online, Mulberry B had landed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. The harbor's performance exceeded even optimistic projections. On peak days, it handled more tonnage than the port of Dover. The flexible roadways proved remarkably resilient, adapting to tides and weather. The Phoenix caissons, though battered by storms, held their positions for months. The entire system, cobbled together under fire and operating in one of the world's most difficult marine environments, kept the invasion supplied through the critical summer of 1944. The Mulberry harbors represented a triumph of engineering and logistics. They proved that with enough planning, resources, and determination, seemingly impossible obstacles could be overcome. The concept of prefabricated harbors influenced post-war engineering, from offshore oil platforms to modern floating terminals. But more importantly, they solved the central logistical challenge of D-Day. Without the Mulberries, the invasion might have succeeded initially, but failed in the subsequent weeks when supplies couldn't keep pace with needs. Today, remnants of Mulberry B still sit off Arromanches, concrete Phoenix caissons visible at low tide, silent monuments to one of history's boldest logistical solutions. They stand as proof that D-Day's success wasn't inevitable or simply the result of numerical superiority. It was earned through brilliant engineering, meticulous planning, and the willingness to attempt what conventional wisdom said couldn't be done. The floating harbors weren't just a technical achievement. They were the foundation upon which the liberation of Europe was built. Modern armies don't march on their stomachs, as Napoleon famously claimed. They roll on gasoline. By 1944, mechanized warfare had transformed military logistics into an equation dominated by a single resource: fuel. Every tank, truck, jeep, aircraft, and generator consumed petroleum products at prodigious rates. The Allied invasion force assembling for D-Day represented the most fuel-dependent military operation in history, and the mathematics of keeping it supplied were terrifying. The numbers told a stark story. A single Sherman tank consumed roughly 1 gallon of gasoline per mile traveled. Multiply that by thousands of tanks, add tens of thousands of trucks, aircraft flying constant sorties, and generators powering field hospitals and communications centers, and the fuel requirements became astronomical. Conservative estimates projected that Allied forces in France would require a minimum of 1 million gallons of gasoline per day just to maintain operations. During major offensives, that number could double or triple. Traditional supply methods couldn't possibly meet this demand. Throughout military history, fuel had been transported in barrels, drums, and later in tanker trucks and ships. For D-Day, this meant endless convoys of tanker vessels crossing the channel, offloading into smaller tankers which would ferry fuel to beaches where it would be pumped into jerry cans and drums, loaded onto trucks, and driven to fuel dumps near the front lines. Every step of this process was slow, dangerous, and consumed precious cargo space and manpower. Worse still, the entire system was vulnerable. German U-boats and aircraft threatened tanker convoys. Storms could delay shipments for days. Beach unloading was slow and weather-dependent, and the jerry cans themselves became a critical shortage. There were never enough of them, and they had a frustrating tendency to leak, evaporate, or simply disappear into the chaos of war. Some estimates suggested that up to 30% of fuel shipped in containers was lost before reaching its destination. British planners recognized this crisis early.
In 1942, as D-Day planning began in earnest, engineer Arthur Hartley and Admiral Louis Mountbatten discussed an idea so audacious it seemed almost comical. Why not lay a pipeline across the English Channel? Transport fuel directly from British refineries to France, eliminating ships, jerrycans, and most of the vulnerable supply chain. The concept was simple. The execution would be anything but. The project received the code name PLUTO, Pipeline Under the Ocean. It would become one of World War II's most ambitious and secretive engineering projects, a technological moonshot developed in parallel with the Mulberry harbors, but requiring even more innovation. No one had ever laid a fuel pipeline across open ocean before. The technical challenges seemed insurmountable, yet failure meant potentially crippling the invasion through fuel starvation. Engineers faced problems that had no precedent. The English Channel averaged 150 feet deep in the planned crossing areas. The seabed was uneven, with rocky outcrops and deep trenches. Tidal currents were fierce, capable of moving heavy objects considerable distances. The pipeline would need to withstand these currents, plus the pounding of storms and the potential for damage from ship anchors, mines, and deliberate sabotage. And it had to pump gasoline at rates measured in hundreds of thousands of gallons per day. The pipe itself required revolutionary engineering. Conventional steel pipe would be too rigid, requiring thousands of joints that would leak under pressure and stress. British engineers developed specialized flexible pipe that could coil onto massive reels, allowing continuous lengths to be deployed without vulnerable joints. Two designs emerged, one using lead-reinforced pipe developed by Siemens Brothers, and another using steel wire reinforcement created by BICC. Both could handle the high pressures required to push fuel across 70 miles of seabed.
Testing began in secret facilities across Britain. Engineers laid experimental lines across Scottish lochs and Welsh rivers, simulating channel conditions. They developed specialized laying ships, converted from obsolete vessels, equipped with enormous drums holding up to 100 miles of coiled pipeline. The HMS Persephone and HMS Latimer became floating pipeline layers, their massive reels looking like industrial versions of fishing line spools. The pumping stations presented their own challenges. Fuel had to be pushed across the channel at sufficient pressure to overcome resistance and elevation changes. Engineers designed powerful pumping stations disguised as innocent buildings. Some were hidden inside fake cottages and bungalows along the British coast. Others were camouflaged as holiday huts or ice cream stands. German reconnaissance flights photographing the British coastline never suspected these innocent structures housed industrial pumps capable of pushing thousands of gallons per hour beneath the waves. On the French side, receiving stations had to be established after the invasion, a logistical nightmare, requiring engineers to go ashore with the assault troops. Teams of pipeline specialists landed on D-Day +1, carrying specialized equipment to establish beach terminuses. Under fire, often working in water, they installed valves, pumps, and storage tanks, creating the infrastructure to receive fuel from England. The first PLO line, designated Bambi, British Admiralty meter-based installation, ran from the Isle of Wight to Cherbourg. Laying began in August 1944, after Cherbourg fell to American forces. The laying ship HMS Conundrum slowly paid out the flexible pipe, which sank to the channel floor behind the vessel.
The operation required perfect coordination between ship speed, pipe deployment rate, and weather conditions. Too fast, and the pipe would kink. Too slow, and currents would tangle it. The moment of truth came when pumps activated for the first time. Would the pipe hold pressure? Would joints leak? Would the system actually work? Engineers watched gauges anxiously as pressure built. Fuel entered the pipeline on the British side and began its journey beneath the waves. Hours later, it emerged at Cherbourg. PLUTO worked. Success led to rapid expansion. Additional lines were laid from Dungeness to Boulogne after that port was captured. Eventually, 20 separate pipelines stretched across the channel, creating a web of fuel arteries feeding the Allied advance. Some lines were only an inch in diameter, others 4 inches. Together, they formed the world's first underwater petroleum transportation network. The system's capacity grew beyond initial projections. Early estimates suggested each line might deliver 300 tons of fuel daily. Optimized operations achieved nearly double that rate. At peak operation, PLUTO delivered over 1 million gallons of fuel directly to France, equivalent to the entire projected daily requirement of Allied forces. This meant that theoretically, every drop of gasoline consumed by Allied vehicles in France could flow through the seabed pipelines, eliminating the need for tanker convoys entirely. The strategic impact was enormous. Every gallon delivered by PLUTO freed up precious cargo space on ships for ammunition, food, medical supplies, and reinforcements. Tanker vessels could be repurposed for other critical missions. The reduction in vulnerable surface traffic made the entire supply chain less susceptible to U-boat attacks, and the system operated continuously, unaffected by weather that would ground aircraft or keep ships in port. PLUTO provided operational flexibility that traditional methods couldn't match. When General Patton's Third Army made its famous dash across France in August 1944, fuel demands spiked dramatically. Pipeline operators simply increased pumping rates, delivering additional capacity within hours. Conventional supply methods would have taken days or weeks to adjust to such sudden changes in demand. The psychological impact shouldn't be underestimated either. German intelligence eventually discovered PLUTO's existence and recognized the technological achievement it represented. The realization that the Allies could lay pipelines across the seabed suggested a level of industrial capability and engineering sophistication that was deeply demoralizing. If the enemy could build underwater pipelines as an almost casual logistical solution, what else were they capable of? Maintenance became routine, but remained challenging. Engineers developed specialized monitoring techniques to detect leaks and pressure drops. Ships stood ready to locate and fix damaged sections. Some damage came from ship anchors dragging across pipes. Other breaks resulted from unexploded ordnance or deliberate sabotage attempts. Each required rapid response to minimize fuel loss and maintain flow rates. The economic calculations proved PLUTO's worth repeatedly. Each pipeline cost approximately £1 million to construct and install, expensive for 1944, but a bargain compared to the alternative. The fuel saved from evaporation and spillage alone paid for the system within months. The ships and manpower freed for other duties multiplied the value. And the operational advantages of reliable, high-capacity fuel delivery were literally priceless in military terms. PLUTO operated throughout the remainder of the war, continuously evolving and improving. Additional lines were laid as new ports fell to Allied forces. Capacity increased as engineers learned to optimize pressure and flow rates. The system that began as a desperate solution to an impossible problem became standard operating procedure, the backbone of Allied fuel logistics in Europe. After the war, PLUTO influenced petroleum industry development profoundly. The techniques developed for underwater pipeline laying directly led to offshore oil exploration and production technologies. Modern subsea pipelines carrying oil and gas across continental shelves owe their existence to engineering breakthroughs made in the rush to supply D-Day. The entire North Sea oil industry traces its technical lineage back to those first experimental pipes laid across locks in Scotland. Today, sections of PLUTO pipe occasionally wash ashore on channel beaches, corroded remnants of an engineering marvel. Most of the system remains on the seabed, gradually being covered by sediment and forgotten. But for 10 months in 1944 and 1945, those pipes represented the difference between success and failure, the invisible arteries that kept the Allied advance rolling toward Germany. PLUTO embodied everything that made D-Day's logistics revolutionary: bold vision, innovative engineering, meticulous planning, and flawless execution under impossible circumstances. It proved that with enough ingenuity and determination, even the most fundamental limitations could be overcome. The invasion didn't just need courage, it needed pipelines running beneath the waves, carrying the lifeblood of mechanized warfare directly from England to France. That this system not only existed but exceeded all expectations stands as a testament to the extraordinary logistics that made victory possible. By August 1944, the Normandy invasion had succeeded beyond the most optimistic projections. Allied forces had broken out of the bocage hedgerows and were racing across France at speeds that astonished commanders on both sides. General George Patton's Third Army advanced 50 miles in a single day, liberating towns faster than maps could be updated. The German army was in headlong retreat, desperate to reach defensive positions along the German border. Victory in Europe seemed tantalizingly close. But triumph was breeding its own crisis. The Allied armies were advancing so rapidly that their supply lines couldn't keep pace. The Mulberry harbors and PLUTO pipelines delivered supplies to Normandy efficiently, but Normandy was now 200 miles behind the advancing front lines. The distance grew by the day. Supplies piled up on Norman beaches, while soldiers at the front ran dangerously low on ammunition, food, and fuel. The entire offensive threatened to grind to a halt, not because of German resistance, but because of the tyranny of distance and logistics. The core problem was transportation. Allied bombers had systematically destroyed French railways in the months before D-Day, preventing Germans from moving reinforcements, but now preventing the Allies from using rail to move supplies. The French road network was inadequate for the volume of traffic required. Captured German vehicles were incompatible with Allied fuel and parts. And the advance had been so rapid that plans for establishing forward supply depots had become obsolete before implementation. Conventional logistics doctrine was failing. Supply officers calculated that maintaining forces at their current positions required 20,000 tons of supplies daily to reach the front. At current delivery rates, they could manage perhaps half that amount. The deficit grew each day. Fuel shortages were particularly acute. Patton's tanks, advancing deep into France, were literally running dry. Ammunition stocks at the front dwindled to dangerous levels. Medical supplies ran short. Even food became scarce as combat units outran their supply columns. The solution emerged from necessity and desperation. A massive, round-clock truck convoy system operating exclusively to rush supplies from Normandy beaches to forward dumps near the front lines. The operation needed a name, and someone suggested Red Ball Express, borrowing railroad terminology where Red Ball freight indicated high-priority cargo. The name stuck, and within days of conception, the Red Ball Express became operational. The system's design was brilliantly simple. Designated routes, marked with red balls on signs every few miles, would be reserved exclusively for supply trucks. No other traffic allowed, no exceptions. Trucks would run in continuous convoys, traveling one direction on one route, returning empty on a parallel route. Drivers would operate in teams, alternating between driving and rest, keeping trucks moving 24 hours per day. Speed limits would be ignored. Safety regulations would be relaxed. The only priority was getting supplies forward. Implementation began on August 25, 1944. Within 48 hours, over 5,000 trucks were operating on Red Ball routes. The convoys stretched for miles, a continuous stream of deuce-and-a-half cargo trucks, each carrying 5 tons of supplies, moving at maximum speed toward the front. At night, the headlights created rivers of light flowing across the French countryside, visible from aircraft overhead. The drivers were predominantly African-American soldiers from the Quartermaster Corps. This reflected the U.S. Army's shameful segregation policies, which relegated most black soldiers to support roles rather than combat positions. But it also meant that the Red Ball Express became one of the few places in the segregated military where African-American soldiers could demonstrate their courage, skill, and indispensability to victory. They would prove exceptional at a job that demanded everything from them. The work was brutal and relentless. Drivers pushed their vehicles far beyond designed limits, racing down roads at speeds that made accidents inevitable. They drove 20-hour shifts, sustained by coffee and amphetamines, fighting exhaustion that made concentration nearly impossible. Sleep came in brief naps during loading or fuel stops. Meals were eaten while driving. The pace was unsustainable, but sustainability wasn't the goal. Speed was everything. Maintenance became a continuous crisis. Trucks designed for 30,000-mile service lives were burning out in weeks. Tires wore through at catastrophic rates, with some trucks requiring new rubber every few days. Engines overheated and seized. Transmissions failed. Brakes wore down to nothing. Mechanics worked frantically at way stations along the routes, cannibalizing broken trucks to keep others running. The express consumed vehicles the way frontline units consumed ammunition. The routes themselves took tremendous punishment. French roads, never designed for such traffic, disintegrated under the constant pounding of heavy trucks. Dust clouds in summer reduced visibility to near zero. Rain turned unpaved sections into mud bogs. Convoys created their own weather systems, generating clouds of dust and exhaust that could be seen for miles. Local French civilians watched in amazement as the endless parade of trucks rumbled past their villages day and night. Accidents were frequent and often fatal. Exhausted drivers fell asleep at the wheel and crashed. Trucks collided in the dust clouds. Vehicles ran off roads on sharp curves. Some drivers, pushing beyond human endurance, simply collapsed. The casualty rate among Red Ball drivers, while not from enemy action, was significant. Every mile of road claimed its price in wrecked vehicles and injured men. German forces occasionally attacked the convoys, recognizing their strategic importance. Luftwaffe fighters strafed truck columns when they could penetrate Allied air cover. German special forces teams attempted sabotage, mining roads or ambushing isolated vehicles. But these attacks were rare and largely ineffective. Allied air superiority made daylight attacks suicidal for German aircraft, and the sheer volume of traffic made interdiction nearly impossible. The tonnage moved was staggering. At peak operation in September 1944, the Red Ball Express transported over 12,500 tons of supplies per day. In a single month, the Express hauled 135,000 tons of cargo, equivalent to loading every truck in the convoy to capacity 5 times over. If lined up end to end, the daily convoy would stretch over 120 miles, a moving supply line longer than the distance it traveled. Fuel for the trucks themselves became a significant concern. The Express consumed enormous quantities of gasoline just to move gasoline to the front. Some calculations suggested that for every 5 gallons delivered, 1 gallon was burned by the delivery truck. This inefficiency would be unacceptable in normal circumstances, but these weren't normal circumstances. The alternative was letting the advance stall completely. The human cost mounted steadily. Drivers pushed themselves into states of near collapse. Medical officers reported cases of hallucinations from sleep deprivation. Men drove with broken bones and injuries that would normally require hospitalization. The determination to keep supplies flowing overcame pain, exhaustion, and fear. It was a different kind of courage than charging enemy positions, but courage nonetheless. Loading and unloading became highly choreographed operations. At the Normandy beaches, supplies were pre-loaded onto pallets and organized by priority and destination. Trucks pulled up, received their cargo assignments, and were loaded in minutes rather than hours. At forward dumps, combat soldiers formed bucket brigades to unload arriving trucks immediately, sending them back to Normandy with minimum delay. Every minute saved, multiplied across thousands of trucks, meant tons of additional supplies reaching the front. The impact on the Allied advance was direct and measurable. When Patton's tanks ran low on fuel in late August, threatening to halt his spectacular advance, the Red Ball Express delivered 300,000 gallons in a single 24-hour period. When ammunition stocks at the front fell to less than 1 day's supply, the Express prioritized artillery shells and small arms rounds, delivering enough to sustain offensive operations. The system bent, but never broke. Competition for trucks became intense. Every commander wanted priority for their sector. Eisenhower himself had to mediate disputes over truck allocation. The Express couldn't supply everyone adequately, forcing difficult decisions about which units received supplies and which had to wait. These calculations determined which sectors could attack and which had to defend, directly shaping the campaign's strategic direction. By late September, the Red Ball Express was showing strain. Truck losses had become unsustainable, with over 40% of the original fleet deadlined for mechanical failure. Driver exhaustion reached critical levels. The liberation of Antwerp provided a port much closer to the front, reducing the distances the Express needed to cover. On November 16, 1944, after 81 days of continuous operation, the Red Ball Express officially ended. Its statistics told the story of an extraordinary achievement. The Express had hauled over 412,000 tons of supplies across France. Approximately 6,000 trucks and trailers were involved at various times, driven by over 23,000 soldiers, predominantly African American. They had driven millions of miles, consumed tens of millions of gallons of fuel, and kept the Allied advance moving during the most critical period of the campaign. The Red Ball Express also highlighted uncomfortable truths about American society and its military. African American soldiers, denied combat roles due to racist policies, proved themselves absolutely essential to victory in support roles. They demonstrated skill, courage, and dedication that made a mockery of segregationist ideology. The Express became a source of pride in black communities and contributed to the growing momentum for civil rights that would culminate in the 1950s and 1960s. The concept influenced military logistics permanently. The idea of dedicated supply routes, priority cargo systems, and round-the-clock operations became standard doctrine. Modern military logistics still employ red ball designations for high-priority shipments, a direct legacy of those convoys racing across France in 1944. The Express proved that with sufficient will and sacrifice, logistical obstacles that seemed insurmountable could be overcome through sheer determination. The story of the Red Ball Express is ultimately about human endurance and sacrifice. While the Mulberry harbors represented engineering brilliance and PLUTO showcased technological innovation, the Express was about men pushing themselves beyond normal limits. It was about drivers who kept going when exhaustion made them see things that weren't there. It was about mechanics working through the night to keep broken trucks running. It was about officers who coordinated thousands of vehicles with primitive communications. It was about doing the impossible because failure wasn't an option. Today, few physical traces of the Red Ball Express remain. The routes are regular French highways, the Red Ball markers long since removed. The trucks were scrapped or sold as surplus after the war. But photographs show the convoys in their glory. Endless lines of trucks stretching to the horizon, dust clouds rising, determined men at the wheels. These images capture a crucial truth about D-Day and the Allied victory. It wasn't won just on beaches or battlefields, but on supply routes where exhausted drivers raced against time and distance. The Red Ball Express embodied the unglamorous reality of modern warfare. Victory requires bullets, beans, and fuel more than it requires heroism. But the men who drove those trucks were heroes nonetheless, demonstrating that logistics, at its highest expression, demands the same courage and sacrifice as combat. They kept the Allied advance moving when it threatened to stall, sustained offensive operations through sheer determination, and proved that the most critical battles are sometimes fought not with weapons, but with wheels, determination, and the refusal to give up.